All right, let's dive right into this explainer. Today, we're unpacking a fantastic piece by Aaron Rose called The Secret Life of Azure. And it tackles a nightmare that literally every single cloud architect, developer, or systems engineer has sweat through at least once: the dreaded, totally catastrophic system outage. But what makes this source material so incredibly engaging is how it actually frames this highly technical problem. It uses this rich, vivid allegory of a grand Victorian library in London. By the end of our time together today, this story is going to perfectly illustrate exactly how you can prevent catastrophic API failures in your own cloud architectures. We aren't just talking about keeping servers running here. We're talking about the art of failing without your users ever even noticing. So we start by establishing the very real stakes of modern system design. And we see this through the eyes of a junior engineer named Timothy. Picture him just looking nervously at the metaphorical wiring behind the library's main desk. You see, the library relies entirely on a primary AI, referred to in the story as the lead planner. Timothy realizes a terrifying truth here. Everything is perfectly optimized, sure, but it all hinges on this one single point of failure. He points out that if Azure has a regional hiccup, or if their primary API connection just goes dark, the library doesn't just slow down a bit. It disappears completely. He tells his senior colleague, "We're one broken cable away from a 404 knowledge not found sign." That feeling of utter dread, yeah, that's exactly what happens when you build fragile systems.
Enter Margaret, the seasoned senior engineer who steps in to completely reframe Timothy's panic. She lays out a stark contrast for him. On one side, you have Timothy's current setup, total outage. She calls this the fragility trap. It's an all-or-nothing game. If the primary system is up, everything is great. If it's down, bam, the user gets a hard error. On the flip side, Margaret introduces her resilient solution, graceful degradation, or simply the fallback. She explains that to achieve true resilience, you actually have to completely abandon the idea of perfection, and instead you have to plan for exactly how you're going to fall.
Let's get crystal clear on what Margaret's strategy actually is. Graceful degradation is the practice of maintaining limited functionality by shifting to simpler models or maybe cached data during a primary failure. In the context of our Victorian library, it means that even if the genius lead planner at the front desk suddenly faints or has to step out, the library never completely locks its front doors on the patrons. The service might not be quite as incredibly nuanced or as brilliant as it usually is, but hey, the users can still check out books, they can ask basic questions, and they get what they need. Bottom line, the system survives. So, how do we actually build this resilient architecture? Let's get into part one, the degradation ladder, utilizing multi-model redundancy. Now, Timothy asks a super practical question. How do we actually know the lead planner is broken and not just, thinking really hard about a complex query? The crucial point here is the trigger. Margaret introduces the concept of a stopwatch. The system measures what's called a P99 latency timeout. If 99% of requests usually finish quickly, but suddenly the lead planner exceeds a threshold, in the specific case 2 seconds, the system takes action. It absolutely does not wait around for an official crash report or a formal error code. Waiting for a crash basically means your user is just staring at a spinning loading wheel, getting more and more frustrated. Instead, at exactly 2 seconds, the system just assumes there's a hiccup and proactively kicks off the fallback sequence. This perfectly illustrates the descent down Margaret's ladder. Step one is our primary, the lead planner. Think of this as a heavy, highly intelligent model like GPT-4o. If that 2-second latency trigger trips, we seamlessly drop to step two, the scout. In a real-world architecture, this would be a faster, slightly less capable model, something like GPT-4o Mini. It might lack all the deep nuance, but it is incredibly fast, and most importantly, it's alive. Now, what if the Scout's API is also unreachable? No problem. We drop to step three, the tiny model. This represents a local, lightweight model actually running in the basement, like Phi-3. The answers definitely get simpler and shorter as we fall down the rungs of this ladder, but the critical takeaway is that the library is still open for business. But Timothy, being a sharp junior engineer, immediately spots a flaw. And that brings us to phase two, the circuit breaker, featuring half-open recovery. Wait, won't this system just keep blindly knocking on a dead API's door, completely wasting time and compute resources on every single user request? To solve this, Margaret describes a heavy cobalt switch. Let's walk through how this works. In a normal, healthy system, the circuit is closed. Traffic flows happily to the lead planner. But if the primary model fails 3 times in a row, the switch trips. The circuit is now open. For the next 5 minutes, the system doesn't even bother trying the primary API. It routes absolutely everything straight to the fallback. It stops knocking on a door that simply won't open. But here's the absolute genius part. After 5 minutes, it enters a half-open state. It cautiously lets exactly one test request slip through to the primary. If it succeeds, awesome, the primary is back online and the circuit closes. If it fails, the breaker trips open again and the timer resets. It's an elegant system that protects itself while remaining cautiously optimistic. Timothy is definitely catching on, but he pushes Margaret to the absolute worst-case scenario. What if the metaphorical basement just completely floods? Let's explore phase 3, the static safety net, which serves as the ultimate fallback. Think of this as a solid concrete floor at the very bottom of the system. When all the computational rungs of the ladder snap, you don't just throw an ugly 404 error page covered in broken code at your user. You serve a specific static text message. The library is experiencing high volume. Please rephrase or try again in a moment. As Margaret notes, it's not an answer to their question for sure, but it is honest. It's a static safety net that catches the users smoothly. It maintains the library's professional facade even when the building is, metaphorically speaking, on fire behind the scenes. And you know, there's one more brilliant psychological trick in Margaret's playbook to maintain trust: degradation transparency. Notice the tiny lightning bolt emoji? Whenever the system is running on the Scout model, or maybe serving cached data instead of fresh processing, she adds this indicator right next to the response. It signals to the user that the system is operating at a reduced capacity. Why does this matter so much? Because trust requires transparency. If a user gets a slightly less detailed answer than usual, that lightning bolt tells them exactly why. They don't think your AI has suddenly gotten stupid. They understand the system is just adapting. It fosters immense user trust because you are being honest when the lights are dim. Okay, so we have the theory down: the ladder, the breaker, the fallback, and the transparency. Now, let's look at the result, failing with dignity, when the library is actually put to the ultimate test in the middle of the night. Late that night, an actual Azure primary region flickers and goes entirely dark. Timothy is watching the dashboard. It turns cobalt blue. The system instantly realizes the latency is too high. The circuit breaker trips, halting traffic to the dead primary API. Traffic seamlessly routes to the Scout model. To the end users, the library just felt a tiny fraction faster, and a small bolt of lightning appeared next to their answers to tell them why. Nobody saw a single 404 error. The system fell, but as Timothy realized, it never actually hit the ground. And this brings us to Margaret's incredible summarizing philosophy. The best systems aren't the ones that never break. They're the ones that know how to fail with dignity. This whole allegory serves as an absolutely vital blueprint for anyone building modern applications today. The internet is unpredictable, folks. APIs will go down, servers will crash, cables will literally get broken. So I want you to look at the architectures you are building right now and ask yourself, is your system ready to fail gracefully? Are you currently trapped in Timothy's all-or-nothing fragility trap, terrified of a single point of failure? Or have you built a degradation ladder, installed a circuit breaker, and prepared a solid concrete floor so that your system, no matter what happens, is ready to fail with dignity? Take these lessons, implement those fallbacks, and make absolutely sure your users never see a 404 error again.